Welcome to Hobby Electronics Club. This is the 67th episode of microcontroller unit. The objective of the present work to display alphanumeric and symbol in WS2812 8x8 color matrix display using the 24C256 EEPROM, which stored with lookup table without using software library. The WS2812B display and its working. WS2812 display overview. The WS2812B 8x8 LED matrix is a 64 pixel addressable display. Each color LED can be controlled individually via a single digital pin using specific one-wire protocol. Here are the complete technical detail and scheme layout and operational logic. Comparison of MAX7219 and WS2812 display. The MAX7219 is a monocolor display, whereas the WS2812 is a 16 million color controlled 8x8 matrix display. The other details are given in this page. 8x8 one module pinout. An 8x8 matrix chain contains 64 individual WS2812B IC in a serpentine or raster grid pattern. The data flows sequentially from first LED, that is pixel 0, to last LED, pixel 63. 1. Hardware pinout. The matrix board typically exposes 3 pins on the input side, 3 pins on the output side for a chaining multiple matrices. 5 volt VCC, positive power supply, GND, common ground reference. D-in is a data in, input signal from microcontroller pin. D-out is a data out, connects the D-in to the next matrix, which is optional. 2. Critical component addition. To prevent damage to the LED, your physical circuit must include decoupling capacitor, a 1.1 microfarad capacitor connected between VCC and ground pin of each individual LED, usually pre-soldered on the commercial matrix board. The data line resistor. A 330 ohms to 470 ohm resistor is placed in line between the microcontroller and digital output pin and the matrix DN pin to suppress the data line voltage spikes. Bulk capacitor. A 1000 microfarad 6.3 volt or higher capacitor across the main 5 volt and ground power supply terminal to handle sudden changes in the current demand. 3. Working principle. The core logic relies on high-speed, time-multiplexed, self-clocking, one-wire protocol. 1. Data structure. 24-bit color. Each individual WS2812B LED contains an internal 8-bit shift register for each of its primary color. To set a color of 1 pixel, you must transmit 24 bits of data in a specific RGB sequence. Green 8-bit, red 8-bit, blue 8-bit. Item 4. Cascading data protocol. The microcontroller sends continuous stream of 64 into 24 bits, that is equal to 1536 bit down the data in line. The first LED in the matrix intercepts the first 24 data to set its own color. Once the first LED internal register is full, it reshapes the remaining signal and passes the remaining bit out through the D out pin to the DN pin of the second LED. This bucket bridge process repeats down the entire line until 64 LEDs have latched their respective 24-bit color data. To lock the color on the screen, microcontroller pulls the data line low for a reset time or time reset exceeding 280 microseconds. Section 5. Signal timing logic. Because there is no external clock line, the WS2812B distinguishes a binary 0 from binary 1 by the duty cycle width of the voltage pulse. Logic low 0, high voltage for 0.4 microsecond followed by low voltage for 0.85 microsecond. Logic 1, high voltage for 0.8 microsecond followed by low voltage for 0.45 microsecond. Item 6. Power consumption requirement. Powering an 8x8 matrix requires a dedicated external power supply if run at a full brightness. Idle current 1 milliampere per LED. Internal control circuit only. Maximum current 60 milliampere per LED when displaying pure white at 100% brightness. Red 20 milliampere, green 20 milliampere, blue 20 milliampere. Total maximum matrix power 64 LED into 64 milliampere is equal to 3.84 ampere at 5 volt. Warning and safety note: do not power the matrix entirely through Arduino or Raspberry Pi 5 volt output pin, as it will overheat or blow the onboard regulator. Use an external 5 volt 4 ampere DC switching power supply, ensuring you can connect the external power supply ground directly to the microcontroller ground. Data format example for displaying A in blue color. To display a blue color letter A on 8x8 WS2812B matrix, you need to transmit data for all the 64 pixels sequentially. The pixel formatting character will be set to full blue while the background pixel will remain turned off. Here is the exact breakdown of the data sequence sent by the microcontroller. 1. Pixel grid layout. Matrix map. An 8x8 matrix contains pixels from 0 to 64 typically in serpentine configuration. The data path snakes back and forth to simplify wiring. Below is the bit layout for a using 1 for blue and 0 for off. One can clearly see that it is similar to the MAX7219 monocolor bitmap. Section 2. 24-bit color data coding. The WS2812B IC expects 24-bit GRB color packets per pixel. For a background pixel off condition, hex 000000 is transmitted. Binary stream of zeros 24 bits is transmitted. For a letter pixel for blue, the hex 0000FF is transmitted through the stream. Section 3, sequential data stream. First 16 pixel. The microcontroller pushes continuous stream of 64 times 24,536 bit because the physical serpentine layout of the matrix row alternate directions. The row 0, left to right, pixel 0 to pixel 7. Pixel 0 off, pixel 1 off, pixel 2 blue, pixel 3 blue, pixel 4 blue, pixel 5 blue, pixel 6 off, pixel 7 off. The 24-bit data transmitted in binary form is presented in this table. The section 4, row-wise data. The row 1, left to right, pixel 8 to pixel 15, pixel 8 off, pixel 9 blue, pixel 10 blue, pixel 11 off, pixel 12 off, pixel 13 blue, pixel 14 blue, and pixel 15 off. The equivalent binary data 24-bit transmitted is presented. Section 5, the complete 1536-bit single wire signal that is transmitted sample is presented in this page. This section deals with the circuit diagram of wiring of the EEPROM, Arduino Uno and the WS2812 display. The circuit diagram of 24C256 and the WS2812 with Uno is given here. Please refer to the previous episode for wiring the 24C256 EEPROM with the Uno. The same circuit configuration is maintained. Only change from the previous edition is the addition of the WS2812 display instead of MAX7219. The wiring map of 24C256 with Uno. The previous episode deals with the complete detailed description of the wiring. Please keep the wiring same as that of it. See that the A4 and A5 pins of Uno is connected to pull-up resistor and the address pin to the ground. Wiring of WS2812 with Uno. The WS2812 panel is having 3-pin VCC, ground and DN. The VCC is connected to +5 volt of the Uno. Ground is connected to the ground. Data in line is connected to the pin number 6 of the Uno. The image of the completely wired EEPROM and the display with Uno is presented here. Lookup table flashed 24C256 EEPROM. EEPROM, which is flashed with the lookup table, is in the previous episode is used. This process of lookup table flashing explained in the previous episode. This is the greatest beauty of the hardware architecture. The EEPROM has full ASCII character set, ASCII from 32 to 126. This is starting at absolute address 0 of 24C256 EEPROM. The WS2812B display engine can read the exact same memory bank that your MAX7219 used. Bypassing the fast LED library. No heavy fast LED or Adafruit NeoPixel libraries used. These libraries add thousands of bytes of compile code overhead. Instead of a tiny ultra-optimized assembly level data shifter function directly inside your sketch to push the color array to the pin 6. The C++ code is given in this section. This is the page 1 of the code. This is the page 2 of the code. This is the page 3 of the code. This is the page 5 of the code. This is the page 6 of the code. It initiates the entire microcontroller. This is the page 7 of the code. This is the page 8 of the code. The entire 8-page code can be copied or typed into the Arduino IDE and executed. If anyone needs a copy of the code, may kindly contact. Working overview. Phase 1, setup and initiation in the code section. When microcontroller powers on, setup function configures the hardware peripheral. I2C bus acceleration is set to 400 kHz speed. Pin configuration, digital pin 6 is set as output. Buffer reset, the 192-byte frame buffer 64 pixel into 3 color GRB is entirely cleaned to 0 using memset, turning all LEDs off. Phase 2, memory retrieval and color mapping. This phase fetches 8-byte font representation of ASCII character from the external EEPROM chip and transform it into visual pixel. The calculating of the memory address. Each printable character in the standard 8x8 bitmap font occupies exactly 8 bytes of data, 1 byte per row, where each bit represents on-off state. The code filters out the non-printable character and calculates the exact memory location using address is equal to ASCII code minus 32 into 8 formula. Phase 2A, burst I2C data fetch. The code targets computed address and executes non-blocking burst read wire requests from function. From EEPROM, fetches the data to download 8 rows of character data directly into a local temporary RAM array called local bytes. Phase 2B, parsing bit into GRB bytes. The code loops through each byte and evaluates every individual bit from left to right using bitmask 80 hex. If the bit is on, it writes 0A green and 0 hex red, 0 hex blue sequentially into a frame buffer. 0A sets very dim USB safe in green color, 4% brightness to prevent the overcurrent issue. If this bit is off, 0, it writes 0 hex for green, red, blue. Phase 3, assembly matrix driver. Because WS2812B protocol require uncompromising 800 kHz single wire data stream, standard C++ loop logic is too slow and unpredictable. This function relies on handcrafted AVR inline assembly. Phase 3A, disabling interrupts. No interrupt, halt all the background system process like internal Arduino millisecond timer. If interrupt triggered mid-transmission, it will delay a pulse with causing matrix to display corrupted colors or flicker. There is a IDE with code image of compiling process. This is the IDE with code image in flashing process. The comprehensive data set of efficiency comparison is of this present work as a research is presented here. One can see 2442 microsecond time frame used by MAX and 1160 microsecond is used by WS2812B matrix display. There is a efficiency and the time saving of the processing is seen. The serial monitor output is captured here. The image of the display sequence is captured and presented in this page. The C++ code for scrolling the text in 8x8 into one matrix tail is given in this section. This is the page 1 of the code. This is the page 2 of the code. This is the page 3 of the code. This is the page 4 of the code. This is the page 5 of the code. This is the page 6 of the code. This is the page 7 of. This is the page 8 of the code. Arduino IDE with code in compiling process captured and presented. The image of the screen of the Arduino IDE with while code flashing is captured. Working of the scrolling text. The working of scrolling logic. The overlap window problem. In single 8x8 matrix, as text moves left, part of the character 1 is disappearing on the left, while the part of the character 2 is simultaneously emerging on the right. The 16-bit sliding register. To handle this shift cleanly, the rendering scroll window function pulls the matching row data to 2 consecutive characters from the EEPROM. It stitches them together into 16-bit integer variable. Bit level shifting. The code calculates exactly how many columns the text has shifted. It shifts the combined 16-bit register left by the offset, masking out the exact 8-bit currently visible inside the matrix plane. Color mapping. The extracted 8 bits are immediately parsed into raw frame buffer. The example above, the brightness variable is routed to the blue channel. The frame buffer scroll brightness function makes the scrolling text shine clean blue. The output. The photos of the letters hello while being scrolled is captured and presented. The efficiency and resource comparison for this method is done with the standard library. The same is presented in the table form. The last column, custom EEPROM reason for success, delists the success story. In general, the comparison to the library, the lookup table method is far better in implementing and saving the time. The advantage of the lookup table method. Ultimate resource conservation. You can run complex multilingual a multi-size display system on a dirt cheap microcontroller with as little as 512 bytes of internal flash. Hardware separation of concern. The code logic lives on MCU. Display visual assets lives on the EEPROM. You can update the font size, symbol, or localize language by simply swapping, or flashing the EEPROM without ever touching or recompiling the main microcontroller code. Deterministic execution. Because the path of the memory to scan is fixed, hardware pipeline screen updates take exact same number of clock cycles every time. This eliminates the jitter in the sensitive timing loop. Glitch-free multi-sizing. Changing from 8x8 font to 4x font is instant and mathematically error-free because the micro characters are pre-baked perfectly into own memory sectors. The limitation of this method. To maintain absolute academic engineering honesty in the publication, you must address the architectural trade-offs. The dual bus bottleneck. Your system relies on two separate communication buses, I2C to fetch data, SPI to push data. If I2C bus is clogged with other sensors like MPU 6050 accelerometer, display update could be delayed. Lack of fluid real-time effect. Because you don't have virtual pixel canvas buffer sitting on the MCU RAM, doing smooth pixel by pixel horizontal scrolling of text or digital graphic animation is highly complex and compared to using a monolithic graphic library. Hardware component cost. It requires extra physical integrated circuit, 24C256 and 2 pull-up resistors on the breadboard, slightly increasing the physical circuit footprint. The serial monitor output while executing the code by fetching the lookup table and displaying is captured and presented in this page. This clearly shows 2.04 microsecond needed for the two action. MAX7219 display versus WS2812 display. 1. The core data difference. MAX7219 protocol. It uses 1 bit per LED. A raw byte like 1C hex is a binary 0001110. It tells the hardware whether an LED is on or off. The WS2812 protocol uses 24-bit 3 byte per LED, 8-bit for green, 8-bit for red and 8 bits for blue. This requires distinct color value for every single pixel. Even if it is turned off, 000 should be sent. The conversion step by step. Let us take an example where row 1 is 1C hex, the row 2 is 22 hex. Your choice, you choose a desired display color in the code, for example pure blue, R is equal to 0, G is equal to 0, B is equal to 255. Step 2A, unpacking of row 1, that is 1C hex. The microcontroller 1C hex into 8 binary bits 0001110. It loops through them from left to right. Bit 7 0 transform to green 0, red 0, blue 0. bit 1 transformed to green 0, red 0, blue 0. When we are planning to display the character in blue, hence bit, you can notice that bit 4, which is high 1, transformed to green 0, blue 0, but blue is full blue color 255. Value is set. This is how each and every bit map for the character is transformed into color information for transfer before transferring into the WS2812 display. Step 2B. Just like unpacking of first row, the second row is given as an example. The HEC-22 is the value to be displayed for displaying the character A for in the second row. The details are given in the bullet points below. 3. The physical layout mapping. A MAX7219 address individual grid natively by rows and columns. WS2812 matrix physically just one single continuous data wire chained from 0 to 63. The indices map depend entirely on your physical matrix layout. 3A. There are two types of layout possible. One is progressive and zigzag layout. In the progressive layout, computation mathematical formula is given here. Pixel is equal to row into 8 plus column. In the zigzag row arrangement of the display, the flexible W2812 matrices wire pixel is like a snake pattern to save space. Row 1 goes to left to right, row 2 goes to right to left. If your matrix is zigzag, the software must reverse every odd row. Row 2 bit 5 normally would be 6th pixel of that row. Because the row runs backward, the software maps it to the pixel 10 instead of 13. Stage 4. Sending data. There are 8 rows, 64-bit total of 8 LEDs. The inner connection specified may be either 3A or 3B. The microcontroller memory contains an array of 1536 bits. 64 LED into 24 bit is equal to 1536 bit. The software library then streams the massive wave of high-speed timing data down the single WS2812 data pin to eliminate the grid. It costs around rupees 650. The packing and courier charge extra and GST extra. If anyone needs kit, may kindly contact. One can contact the author for tips, support, assistance and guidance. Please contact for code and support. Kits are available for learning. Projects for schools and colleges can be designed. Contact the YouTube owner. Subscribe to my YouTube channel. Please subscribe to my YouTube channel by following the link. Thanks for watching. See you in the next episode.